Hey guys, this is Mrs. Lyons. I just wanted to walk you through the lab just to kind of see what you should be doing if you get stuck or if you are not sure. So the first thing you're going to want to do is you're going to want to go to the online textbook. And there, if you go to your class period assignments, you will find this virtual lab. Okay, make sure you find it in assignments so that it records that you have completed the lab. Okay, so let me go ahead. So this is what you will be doing. Okay, so this first page just tells you how to navigate. Okay, important things. There are 5 tabs. Okay, scenario, investigation, analyze, conclude, and extend. Okay, in each of those tabs, you're going to see something like this with the little dots. Okay, if you click through the dots, that will take you through the pages of each stage. So you want to go through the dots first, and then you're going to change to the stage. Okay, up here, if you look up here, this link is at the top right is a lab notebook. Okay, so you're going to type your information into the lab notebook. Okay, so now I'm going to go to the lab. You're going to want to go, and like I said, there are 5 pieces up here: scenario, investigate, analyze, conclude, and extend. All right, so you're going to want to read through. So the first thing it says, you're investigating a group of elements in the periodic table. Your current focus is on the halogens. Remember, the halogens are group 17. Okay. An example of a halogen is the greenish yellow gas inside the flask on the left side of the screen. It says you know some things about the halogens already, including that neutral atoms of these elements have 7 valence electrons because they're in group 17. Unlike their neighbors in group 18, remember group 18 are the noble gases, and they're very, very, very unreactive. The halogens, however, are very reactive. Okay, but the question that we want to answer is, are all of the halogens equally reactive? Okay, or are there other things that we can figure out on our periodic table to determine which halogen is most reactive, which halogen is least reactive? Okay, so we're gonna go on into the second part, which is investigate. Okay, so I'm going to go up here, click on investigate. Notice that there are a couple of parts to investigate. So we're going to click through the buttons before we go back up to analyze. All right, so what it says here, you know what, I'm going to pop back to scenario. Let's see if there's anything I'm supposed. So you might want to type into, so notice what I did. I clicked on the lab notebook. Okay, you might want to just type in here that we're trying to find which halogen is the most reactive. Okay, so I put that in my book. And then I am going to go ahead and close out of my lab book, and I'm going to go to investigate. I'm going to read the directions. Select an object. Select each object to gather information about the halogen samples and how you will test their reactivity using 1 nonmetal and 1 metal. Before you perform the reactions in the fume hood, predict the reactivity of the halogens in your lab notebook. Okay, so we can look here. You're going to click these 4 elements over here in the lab, the virtual lab. If we click that, it tells us those are halogens. The halogens you will test are in different states at room temperature. Iodine's a solid, bromine's a liquid, and fluorine and chlorine are gases. So that's important. Okay, fumes from these chemicals have negative health effects. So all of the reactions are performed in the fume hood. If you were actually in class, we couldn't do this reaction because the fumes are so dangerous. Okay, but the fume hood would draw the gases out of the classroom. Okay, so over here, let's see. So this is where we're going to include, we don't need to look at this yet, but in our lab notebook, we're going to include some data. Okay, We'll go there in just a minute. The second thing that it wants you to look at in the picture, it wants us to look at hydrogen and iron wool or steel wool. Okay, and it tells us hydrogen is a colorless, odorless gas. Iron wool is solid iron shaped in very thin strands, which increases the reactive surface available. And then it tells us react each halogen with two different substances, one nonmetal, which is the hydrogen gas, and one metal, which is the steel wool. That'll help us figure out what is more reactive. Okay, now I'm going to go down here to the second dot. Okay, that's kind of the way that it wants us to progress. All right, and it tells us about two properties. Okay, the first one is the atomic radius. In other words, the size. I always use the size. Okay, and size, it's really small. But if we click on atomic radius, all right, we come over here and it talks about what is atomic radius. It's the distance from the center of the nucleus to the outermost electron shell, so the valence shell. Okay, it was really hard to do this. So one way they did it was to look at bonded atoms. We're not going to really worry about that right now. Basically, what we want to know is that the atomic radius, when we're talking about that, we're really talking about size. Okay, and it tells us, notice it gives us some values for atomic radius here. And we want to record those. So, and I don't know about you, my memory is just always slow. So I'm going to write these down. So I've got iodine, bromine, fluorine, and chlorine. Iodine's radius is 133. Bromine is 114. Fluorine is 64, and chlorine is 99. So the reason I wrote those down on my paper is because I have bad memory. Oh, but I want to go, actually I want to do this on page 2 of my lab notebook. Notice it gives us a place where we can type in the atomic radius. So for fluorine, I said it was 64. Chlorine is 99. Bromine was 114. And iodine is 133. Okay. So I'm going to save that information. All right. Hopefully that saved. Did that save? Let's see. It did. Okay, good. So now I've got atomic radius. I have those values. Okay. So now I'm going to close this and notice over here it says electron affinity. Okay. We're not going to talk a lot about electron affinity, but in this scenario, what it is a measure of how much energy is either absorbed or released when an electron is added to an element. Okay, so the key thing that we want to look at, again, we're comparing trends here. So what we really want to do is we want to write down these numbers. So iodine is minus 295. Bromine is minus 325. Fluorine is minus 328. And chlorine is minus 349. So let's go over to my lab notebook again. All right. And again, we got to go back to page 2. I'm not sure why they did it that way, but it is what it is. So I'm going to type in my values. Minus 295 is, whoops, that's not right. That's iodine. So let's take it down here. Minus 295 is iodine. Bromine is minus 325. Chlorine is minus 349. And fluorine is minus 328. Okay, so we're just recording these so that as we work our way through the lab, we can kind of see, does this have anything to do, do these numbers have anything to do with how quickly a reaction happens? Okay, so I'm going to close my lab notebook again. I have gone through, I'm going to close this. I've gone through everything I need to investigate here. So the next thing that we're going to do is analyze. Okay, so what we're going to do is it's going to ask us to do the lab. Okay, so the first thing you're going to do is you're either going to choose steel wool or hydrogen. Let's just go ahead and take steel wool. We're going to put it up here in the test tube. Okay, and then we need to combine that. There are 4 different halogens: iodine, bromine, fluorine, chlorine. Okay, so we want to add each of those one at a time. So let's do fluorine, because fluorine's the top one on the periodic table. So I'm going to put fluorine up here. And then what you've got to do is you have to turn on the Bunsen burner. Okay, and then what's going to happen is it's going to give us a close-up view. What we want to do is we want to figure out the time it takes. So in this case, this is the steel wool and the fluorine. So let's see how quickly it reacts. Notice that there's a change going on. There's gas being released. And it tells us that it took 2 minutes or 2 seconds for that to react. So now I'm going to go back over here into my lab notebook. I just reacted fluorine with iron wool, and that was in seconds. And it told us that it was 2 seconds it took to react. Okay. Now we're going to go back and we're going to close this window and we are going to reset. And then we're going to do it again. I'm going to do steel wool in the test tube. This time I'm going to use chlorine. Okay, so I drag it up there, turn on the Bunsen burner, hit go, and watch how long. And now you can see it's reacting. It doesn't look like it's reacting quite as quickly as the fluorine did, but notice it says 3 minutes and 3.98 seconds. Okay, so I'm going to go over here into my lab notebook and I'm going to put what did I just say that was? 3.98? Is that right? My memory, 3.98. Yes, okay. So I make sure I got that right. 3.98 seconds. Okay, now we're going to go back. Close this window. Hit reset. We're going to do steel wool. All right. And we're going to do bromine, which is the next one down on the periodic table. Turn on the Bunsen burner. And let's see what happens. Notice it's taking it a lot longer for it to react in the test tube. So 6 seconds. So I'm going to go to my lab notebook. I'm going to look at bromine, and I'm going to say it took 6 seconds. All right, and then finally, we need to do reset. We're going to do steel wool, all right? And we're going to react it with iodine. That was the final combination with the steel wool. Okay, so then we're going to turn on our Bunsen burner. And let's see, iodine and steel wool. Taking very much more time to get that reaction to happen. So 8 seconds. All right, so I'm going to go over into my lab notebook. I am going to say that it took 8 seconds. Now let's see, did I do something on page 3? Ooh, I forgot. We were supposed to estimate what we thought. So hopefully we've done that because we've gone over it in class. Otherwise, we want to say which is the most reactive, which is the least reactive. Okay, so maybe I would say chlorine, bromine, iodine, because that's in order. So I might say that. All right. And then so we've done the steel wool. What I want you guys to do on your own is to go in and do the other combination. So I want you guys, you'll reset, you're going to do hydrogen gas and then the 4 different halogens. Okay. So now, and then you're going to put that data into your lab notebook. Okay. And then we're going to move on to conclude. Okay. So what we're going to do here is we are going to say, were your predictions correct about how quickly they react? Explain your answer. Okay. We're going to go to dot number 2. And it says the valence electrons in atoms are shielded from the attractive pull of the nucleus by inner shells of electrons. This is called shielding. Do you think the reactive of the halogens relates to the shielding effect? Yes or no? Okay, so in other words, we have a number of different energy levels. The question is, based on the number of energy levels, does that change whether the reaction is faster or slower? Okay, third dot gives us a new scenario. Sulfur, which has the symbol S, is a solid at room temperature. It can accept electrons to fill its valence shell just like the halogens. Based on the electron affinity trends on the periodic table, so this is talking about electron affinity, saying it increases towards the top and it increases towards the right, okay? And it's asking us, do we think that sulfur, which is right here, okay, sulfur, is that going to react more or less than fluorine did with the steel wool? Okay, so it's asking you to kind of make a guess. All right, and then finally, we've gotten through our dots. We're going to go to extend. And it says, this three-dimensional version of the periodic table shows ionization energy trends. Ionization energy is the energy required to remove an electron from a neutral atom. Ionization trends across periods are generally more consistent than electron affinity trends, although both are useful. Use what you observe about ionization energy to explain why the halogens do not form positive ions. In other words, why do the halogens, why don't they want to give away an electron? Okay, why is that? Okay, so just kind of it's a thinking question. Use this space to sketch your ideas and solutions. Take a screenshot of your work. So you might want to draw a Bohr diagram and put in there and show that as the electrons get farther and farther from the nucleus, the reaction is going to go quicker because it's easier to remove. All right, and then let's see, we forgot to go back. Let's look at what we need. So we've got our data on slide 4. Slide 5 just has you type some notes. What did you see? Which one was faster? Which one was slower? All right. And then page 6, again, if you have notes, you're going to put them there. Okay, so that's kind of a walkthrough of the lab that you guys are going to do. We're going to start it today in class, but I did just want to give that to you. So kind of if you know you're not sure when you get back to start it on your own, you can then have something to refer to. All right, have a great day.